Hi, I'm Taketo Sano. I'd like to give an introduction to TQFTs from a mathematician's viewpoint, and I hope this will give kind of brief introduction to today's seminar from learning. So, a TQFT is a short for topological quantum field theory, and this is a foundational concept in both physics and mathematics. But the way it is described are pretty different. So in physics, a TQFT is a special QFT that is invariant under the deformation of spacetime. So in other words, it's a QFT that doesn't depend on the metric of spacetime. So okay, so this is how physicists understand TQFT, and mathematicians say a TQFT is a tensor functor or a symmetric monoidal functor from the category of n+1 dimensional cobordisms to the category of vector spaces. So, well, mathematicians are happy with this definition, but I think everyone else is not happy with this definition. Today, I'd like to build a bridge between these two descriptions, and then hopefully, I think you get an intuition of what this is trying to capture from this physics description. And I also think this is a very fun thing to play with. So first of all, this is a short for cobordisms. So in general, a category consists of objects and morphisms. So in order to describe a category, we have to specify what a object is in that category and what is the morphism is in this category. So this category, so here we fix this dimension L. So here we consider this n+1 dimensional TQFT. So a object in this category is a closed n-dimensional manifold. So here we are drawing this as if this n is equal to 1. So here's this one object here, and there's another object like this. So here we're considering this as a discontinuum of two closed objects, manifolds. So these are objects in this category. And also in a category we have morphisms between objects. So that's something like a relation between objects. So what is a morphism in this category? It is a n+1 dimensional manifold that has boundary, the source object and this target object. So this is what this category is. And when we say a functor, it is a mapping from one category to another that maps a object in this category to an object in this category, and also a morphism in this category to a morphism in this category. So if we're given this functor z, then it maps a object in this category. So here, suppose we have this n-dimensional manifold, and if we have this z, then this maps to z of x. And this is a object in this category. So this is a vector space. So here we're considering this field as R, but if you like other fields like C or Q, then you're free to change that to your favorite field. And then here we have another object, so this will be to Z1. So this is a correspondence between of the objects. And furthermore, we have this one-dimensional higher manifold that is bounding both this x and y. And if you're given this, then this functor also maps this morphism into a morphism in this category. So what this cobordism is mapped to is a morphism like this. And the morphism in this category is a linear function, linear map between vector spaces. So this is a linear map. So it's as simple as this. So a closed manifold gets mapped to a vector space, and a cobordism between closed manifolds gets mapped to a linear function, linear map between the two vector spaces. And now we have other adjectives. So first, in this category, morphisms are identified up to boundary fixing deformations. So if we deform this like some other way with this boundary fixed, then they has to map to the same map. So this relation captures this part. It's invariant under the deformations of spacetime. And also this tensor factor, this thing here. So there's this kind of tensor product in both of these categories. So tensor product in this category is this joint union here. And the tensor product in this category is the ordinary tensor product of vector spaces. So what this means is that if we have a disjoint union of two closed manifolds, then the target is a tensor product, the tensor product of two corresponding spaces. So this can be, so the way to understand this is, so we have these n-dimensional, this is something like the space or a state. And we can think of this one-dimensional additional dimension as a time direction. And now we have this deformation invariant coming from the morphism from here. So this corresponds to this invariant under spacetime, deformation of spacetime. And we also have this this functor preserving this tensor product. This means that if we have a independent system x1 and x2, then the corresponding vector space is going to be the tensor product of these. So I think we usually see this in quantum computings. So we have this. If two systems are independent, then the corresponding vector space is going to be the tensor product of the two. So that's encoded in this. Yeah. So the nice thing about this formulation is that this captures the thing that's supposed to be encapsulating this idea into this mathematical formulation. And this is due to mathematician here. Yeah. So today I'd like to play with this definition. So from this we can get a lot of nice mathematical things out of this. Just this very simple definition. So here a TQFT Z gives rise to an algorithm. So this is a very fun thing to play. So now I'd like to restrict to n equals 1. So objects are one-dimensional manifolds, closed manifolds, and morphisms are two-dimensional surfaces between these one-dimensional objects. So let's think about this very simple example. So here, an empty object or an empty space is regarded as an object in this category, and this is a unit. So we have empty here, and we have this surface. So this can be regarded as a cobordism from the empty space to a circle. And then if you're given this functor z, then we can map these objects and this morphism into the category of vector spaces. So first, this z of empty. So this is a monoidal unit. So this should correspond to the monoidal unit in this category, which is the base field R. So this is R. And then this surface, this circle, maps to some vector space, and let's call this A. And then we have this cup that maps from here to here. So we should get a linear map from R to A, and let's call this iota. And what's nice about this category of cobordism is that we can always consider the reverse direction. So if you have this, then we can instead consider the other way. So we also have this map from A to R, and let's call this epsilon. Yeah. And similarly, let's consider this coordinate. So this is a disjoint union of two circles and one circle. So this is regarded as a single object, disjoint union of two circles, and then we impose here that this preserves this tensor product. So this thing here should map to Z of two circles. This should be the tensor product of this vector space and this vector space. So this is A tensor A. And here we have this circle, say. So this surface gives a mapping from A tensor A to A, and let's call this N. And again, if we consider the other direction, then we get a map, linear map from A to A tensor A, and let's call this delta. And these four maps, iota, epsilon, and m and delta, this gives rise to an algebra. So I'd like you to guess what these relations are called. So if you recall from junior high school or high school mathematics, I think you know what these are called. So first we have this trivial cylinder. So this is a circle, cylinder from circle to circle. And then we just deform this a bit, we turn this into this. So I think you can agree that this and this are identical morphisms in this category. So this should map to a same morphism in the category of vector spaces. And do you know what this is? The corresponding thing is in the category of objects. Do you know the name of this law? So this is called the unit law. Because here, let's consider we have this input. We put this input like this. We have x. We have x here, and let's name this the image of this as 1. So we have 1 here. So what this says is that x, this going directly to x, is equal to x with 1 being multiplied and then to x. So this is essentially saying x times 1 equals x. So this is what unit law is supposed to be. This 1 is a multiplicative unit. So we get this, we have this 1 inside this base field. And then we can write this image as a stick 1. And then with this means that multiplying 1 to x is equal to 1. So we automatically get this unit law from this. Now we have this. So do you know what this law is about?
Social.
Yeah, exactly. So yeah, this is called the associative law. So we have this x, x, y, z. So what this is multiplying x times y and then multiplying y, z here. So this is x times y times z. And here we have x. First multiply y and x, and then we multiply x. So we have x times y, z. And because this is diffeomorphic, these two must be equal. And that's what's called the associative law. So now I think you know this one. So do you know what this is? Yeah, exactly. So this is commutative. So we have x here and y here, and x, y here. And this is x times y. And here we have y times x. So this is y times x. And this is supposed to be equal. So this is the commutative law. And here we have another strange kind of looking relation, which is called the Frobenius relation. But this is some kind of compatibility between the product and the coproduct. So we have x times y going out into some coproduct. And this is the same as putting x here and then splitting this into and then merging these two into the same thing. So this identity is called the Frobenius relation. And again, if we consider the reverse direction, then we get this, the identity in the other direction. So we get the dual relation. So if we put x here and consider what's the outcoming result in this side, this is something called the co-unit law. And similarly, we get this co-associative law. And also we get this co-commutative law. And then this is same if you flip up the other side. So an algebra that satisfies these relations together with these maps are called commutative Frobenius algebra. And what's very fun is that in some sense the converse holds. So and vice versa. Then n plus 1 equals 2. So this means that if we start from this TQFT Z, then we get this commutative Frobenius algebra A. But we can start from a commutative Frobenius algebra and then we get this TQFT. This is because every surface can be decomposed into these elementary pieces, and if we define how these elementary objects and these elementary morphisms map to with these laws, then it gives a well-defined function, a functor from the category of two-dimensional cobordisms to the category of vector spaces. So we can get the other way. So if we have a Frobenius algebra, then we get a TQFT for free in dimension 2. So I'd like to show you an example of this calculation. So if you attended the special seminar we had a couple of last month, I think you saw this example where he introduced this homology ring of S2. So I'd like to recall that. So here I like to start from a Frobenius algebra and then define this TQFT. So if you're familiar with the round cohomology, then you can think of this as a round cohomology with coefficients in this reals. So this S2, this is just a two-dimensional sphere, and this is identified as a complex projective line. And the cohomology ring of this is two-dimensional. So we have one generator in degree 0 and one generator in degree 2, which we call this by X. So this X is the first term class of this complex projective line. Now, we get this Frobenius algebra from this. So first, this unit, this is simply mapping this unit 1 in R to this unit in A. So this is the unit. And we have already have this multiplication. So this is a cohomology ring. So it is already endowed with this multiplication. So this is, if you're familiar with differential forms, this is the wedge product of differential forms. But here it's very simple because we only have these two generators. And this one, this is just one in this gradient 0. So we have 1 tensor 1. This goes to 1. So this is just 1 times 1 equals 1. And we also have x tensor 1 and 1 tensor x. This is just 1 times x equals x. And we also have this x tensor x. So this is x squared. But because this degree of x is 2, and we don't have higher degrees, x squared is just 0. Because this should be degree 4, but there is no degree 4 element in this homology ring. So this is what it is. So we can write this as an algebra like this. And in Cobordism, I think you've seen this. If you've seen it, I think you've seen this description. So this comes from the cohomology ring of this sphere. And this is the algebra structure. And we also have this co-algebra structure. So here we have, this is the cohomology ring of this sphere. And here we have this integration over S2. So what this is this maps the top cohomology class X to 1. If you integrate this top level cohomology class over the sphere, then we get 1. But this one, this is just 1. So if you integrate this, it doesn't match the dimension of this sphere. So this 1 goes to 0. So this co-unit is the integration over the sphere. And if we have these, then we automatically get this co-multiplication such that it satisfies this. And the way we define this is this 1 goes to 1 tensor x plus x tensor 1. And this x goes to x tensor x. And then we get a commutative Frobenius algebra. That means we get a two-dimensional TQFT for free. So let's try to use this to evaluate the scores. So this is a closed two-manifold. So this can be regarded as a cobordism from the empty space to the empty space. And this should be a linear map from R to R, which is represented by a number. So a linear map from R to R is just a number. So the value of this should be the value that's coming here. So now let's try. So let's start from this empty set. So let's match this thing, whole thing with Z, and then we get this Z of empty. This is R, and starting from here, we should get to Z of R, empty, which is R, and we compute the coefficient. I mean the how many times this one gets multiplied by this map. So we start from empty, so we start from 1 here. And then we first have this unit. So this 1 gets mapped by this unit to this 1 in A. So this is 1. And then we have this co-multiplication. So this gets mapped to this one. So we have 1 tensor x plus tensor 1. And now we have this merge, so this is a multiplication. So if we multiply this, then what we get, 1 times x is x, x times 1 is x. So if we add the 2, then we get 2x. And finally, we, so this is delta, this is n, and this is epsilon. So finally, if we evaluate this, then this 2x, x goes to 1, so this goes to 2. So the evaluation of this torus is 2, and this 2 corresponds to the dimension of this Providence algebra A. And this holds in general. So if you have a two-dimensional TQFT, then the evaluation of a torus always gives the dimension of this Providence algebra. So this is something to talk. Thank you very much.
Okay, thank you very much. So first the questions from non-experts. Yes.
But I'm a non-expert on this side. So.
Thank you very much for beautiful explanation. But I still don't understand the relation between the physics and mathematics. From physics side, the topological field theory, probably one interesting aspect is the boundary of the two regions with different topological number or something. And to the dynamics would be interesting. And how do you describe in the mathematical side this dynamics? Boundary dynamics.
When you have boundary on the object, do you mean?
Yeah, boundary between the two regions with the different topological invariants. So if it's the spontaneous symmetry breaking, it's very visual. The domain wall or strings. Such a structure is very important in cosmology, and you can visualize it. But the topological quantitative it is much more invisible. But the boundary something exists, I believe, and the dynamics will be interesting. How do you describe from mathematical side this dynamics?
So when you say boundary, you mean the boundary? So is it like the open string and the closed string case? You mean boundary? Which so these are boundary of this multism.
Please,
when you say boundary, is it about boundary of the object?
Oh yeah. Open string.
Oh, the open. So yes. So in this case, the object in this category is a closed manifold. So this object doesn't have a boundary. But more generally, we can think of a extended version. So in the case of n equals 1, which is n plus 1 equals 2, here we just consider this closed string. So we can think of this as a string, but if we consider closed open string as well, we have something like this. So this can be regarded as a one-dimensional object with zero-dimensional boundary. And of course, we can think of a cobordism between such objects like this. And then we can have something like this. And this is if we want to formulate this mathematically, then this is not enough. So we have to think of something called the extended TQFT. So in this category, we only have things of dimension n and n plus 1. But here we have this object of dimensional 0 and dimensional 1 and dimensional 2. So in order to capture this thing mathematically, we have to think of something called the 2 category. So this is just a 1 category. So if you want to formulate this mathematically, we have to think of something called the 2 category. And in general, if you want to consider the extended TQFT in full n dimension, then you have to think something called the fully extended TQFT, which is an n category.
I see. Boundary can also be described by cobordism.
Yes, yes. So this is some kind of curve. So this is like a cobordism between cobordisms. So it's that this one is one dimension is a cobordism between these 2 points, and then we have this cobordism.
Thank you very much.
Yeah, questions from biologists?
I'm a biologist. So we ask maybe a mud question. So here you say that the 2 TQFT is essentially the same thing as a commutative probability algebra.
Yes.
So in a n+1 TQFT, is it something that has an algebraic structure?
So I think it's much more complicated. So the reason why this is so simple is that there's this thing called the classification of purposes. So in particular, the oriented surface is, if you just consider the closed case, it's just classified by these number of holes. We have this. And we can easily say that these pieces can be constructed from these unitary pieces. But as we go one step up, there's no nice classification result for 3-dimensional or 4-dimensional height. So that's why it's much more difficult to do the other way. So we do get a probabilistic algebra from any TQFT, but if you want to like classify these, then things are way more difficult. And I think
But it's more like in the other direction. If you take your n+1 TQFT,
yeah,
you have this nice definition, but that is not very practical. And does it correspond to some mathematical structure that exists? So when n equals 2, it uses the commutative probability algebra.
yeah, I think it's already nice enough, because if you have this, then you automatically get an invariant of n+1 dimensional closed manifolds. So if we have, so suppose we have this closed manifold like this, and then if you have a nice functor like this, then we automatically get this invariant, this. And this is automatically a diffeomorphism invariant. So if you succeed to construct this TQFT, then I think that's already very nice.
Okay.
And yeah, so for example, if you want to, so suppose we're thinking about 4-dimensional manifolds, and we want to have some invariant like this, then if we could extend that as a TQFT, then the computation of this invariant breaks down into the computation for each of these pieces. So we start from a empty, and then we have this boundary 3-dimensional manifolds, and then we just compose these maps to get the whole invariant like this. So in general, if this is a useful functor, then it is already something very good.
Okay.
Yes.
So I want to ask him, what's the importance of TQFT? Some topological invariant or some algebraic relations, or you just want to study the QFT, the curves type?
You mean in mathematics? Or
I don't know in mathematics that physics. What's the importance?
yeah, in physics, I think you should ask. But in mathematics, I as I just said here, so if we have suppose we have a numerical invariant like this, and we want to compute this, but if this closed manifold itself is extremely complicated, then it's very, very hard to compute. But if you can break it into pieces like this, then you can reconstruct the invariant from this. So it's like taking I think this is very much like the quantum people draw something like this, and we have and then we have some kind of thing that's going inside here. We have this unitary thing like this. So this is very similar. So we have empty here, and we have empty here. It's like taking the inner product between the two. So I think essentially, I mean, conceptually, the things looks very much the same.
So can I understand this? For example, if you have a Q3 theory or other alternative theory, you can separate it to some simple theory.
Yeah, if that's succeeds, then that's very nice thing to have. And I think that's yeah, maybe yes,
Oh.
yes. And I think that's
exactly it is. So since where it is invariant and as well you wrote where local deformation of the metric or so it is this information is independent of the details of the for example field theory or so some quantities in field theory including some non-perturbative number counting or that can be very easily calculated using this kind of method. So in physics, where always several people are experts, but in physics it is useful.
Yeah.
So I hope that I hope that why it is so important in mathematics.
so. I think it's the same thing. So so suppose we have an invariant for closed manifolds. It's nice if we can decompose this into pieces so that we can compute this by composing these elementary pieces. And we can also think, so if you have a invariant of 4 manifolds, and then we succeed to extend this as a TQFT, then we get this relative invariant as the linear map between vector spaces. So this linear map itself is an invariant of this 3-dimensional object. So, and that's something that we see in Sandon theory and cyberbulletin theory in mathematics. So yeah, we get more information that can be computed by breaking down into elementary pieces. And each of these pieces, these things itself, these are invariant of the 1-dimensional low manifolds. So I think so. This example is supposed to be a vague example of that. So suppose we have, so this might be a topologically. So so a torus can be something very complicated, like this, and we might have a very big genus like this. And if we know that this is a torus, then we can deform it into a simple shape like this, and then we can easily compute it like this. So yeah, so this is supposed to be a vague example of a computing the expectation variant of this.
So does it answer to your
Well, from
Okay, suppose and I don't know this stuff at all, but suppose n is bigger than 2, for example, and I want to understand your statement like A topological QFT gives rise to an algebra.
Yeah.
And if you have n equal bigger than 2, for example, 3,
yeah,
and you don't have maybe classification may not be. But anyway, that still has some topological one of the theories say no boundary on the boundary. And closure space, and it'll give some algebra. That's the statement, right?
Yes.
So always.
Yes.
And then in principle, you got to know these algebra.
Yes.
Then what's the statement, the meaning statement that the other, because if you figure out algebra, then that algebra corresponds to n equal 2 thing, right?
yes, in this case, yes.
Yeah. So what's your statement that the other direction is not you can say something like the other direction is not true also. Is that true?
I mean,
Because vice versa only when n plus 1 is 2.
yes. So the reason why n equals 2 succeed is that the surface decomposes into very simple pieces.
Yeah.
So we can just use these as the building block.
I understand.
But if you go one dimension higher, we need something like a classification of 3-dimensional manifolds, and that's obviously not easy. It's not as easy like this. So
Yeah, but so you may not know exactly, but is that the statement? Like if you know it exactly, that corresponds to.
so in general, if you want to go the other side, you have to I don't know if there's a theory, but you have to put much more construction
Yes.
on this thing to get the TQFT. And I think so. Today's talk will be about 3D TQFT. So I think there'll be some.
Is there any meaningful question as, for example, if you have any like combinatorial Frobenius algebra, you may have corresponding QFT topological.
Yes, I think so.
or something like
I think
that.
that's a very meaningful question. So if,
Yeah.
if you have whether if you're given a so this. So in general, we get a TQFT. I mean a Frobenius algebra for free. So instead of considering this S1, we can think of this S of n, and then if it's a sphere, then we can always merge this into the sphere. And if it's some kind of arbitrary manifold and there's a sphere like this, then you can always move this thing. So this things become a module. So we do get some if we get this, then we do get this nice thing. And the question is, if we have this Frobenius algebra and this collection of A modules, then do we manage to get this TQFT? And I don't know the general answer, but I think that's meaningful and very
Maybe some rule on the boundary. Some you may have to put some restriction on the boundary or something.
Yes, I think so.
Different so, but if you can always consider something like that restriction or not.
I don't think it's always possible. So the construction itself, I think, is very non-trivial. So if we do manage to construct this TQFT from this, starting from this, then I think that's a very interesting result.
It's already an expert question.
So let me ask a very stupid question from biological viewpoint. And in bacteria, we have a circular DNA. So that's kind of circular DNA sometimes have unified to another circular DNA or the divided into two. So do you think we can formulate such kind of event using this kind of mathematical? Yeah, I don't know how it is useful.
So the circular DNA is something like a
Yes, circular. Yes.
it's a knot. And
Yes. And sometimes it is unified to another circular DNA.
so we have two of these.
Yes.
merging.
Yes.
Also,
Yes.
that's exactly so. Yeah, so that's exactly what I'm doing.
Yeah. And in that sense, what we want to know is the previous state. Previous state. In the so what was the sequence was like in the 10,000 years ago or something.
I see.
So then, is it so? What do we need to estimate the previous state of the sequence on such kind of circular DNA using this formulation?
Yeah, I think that's a very interesting question. So when we consider, so we have this knot. So this is a one-dimensional. Okay. So this is the circular DNA.
But never observe not DNA.
So it's trivial.
Trivial circular. Sorry for not.
But I had some where the statistical physicists were studying such an
Okay.
not in the biological.
Okay. Yeah.
And I also think if this thing and this thing is regarded as something different,
Yes.
then you shouldn't consider this topological. That maybe you should take into account the metric
Okay.
or what's inside this thing. So if you want to apply mathematics to that situation, then we should not consider topological, but we should take into account the information that's inside here.
Okay.
So in biology, probably this doesn't have a direction of time concept. So if you set up it like if you DNA merge or split, in that case, both gives like some amount of some material or something, and you want to count the final material, then it's probably the same thing.
Yes.
I mean, you need
Yeah, I agree. Yes.
The question is very interesting because even if it's not the TQFT, we have something like this, and then we have this merged into something like this. And then we can consider the corresponding spacetime like this. Yeah. And the question is, if you're given something here, then can we get something back here? So it's exactly, so if we have a map like this, then do we get a solution by this? So if we have y here, then the question is whether we have x in the original space such that is y is fx.
But we need to know about that such kind of functor. Yeah.
Yeah, so
So we need to know f, right?
yeah, so
For that.
in nice case, this kind of thing gives a restriction of this.
Yes.
So we can say we maybe not be able to fully recover this back here, but maybe we can say that this never comes from something here. So that's one nice way to use this kind of factor here.
Okay.
Yeah, so topological, I think field theory is often very useful when we want to calculate something very difficult to calculate in a theory with some parameter. But now it can be, it becomes easy to calculate in a very special limit of the parameter. So in such a way, in physics, that's a usage of topological field theory. So maybe if you want to calculate something like that, then you can use that lesson. Yes?
Okay, I have a question. It's perspective, I took the figure, we are writing the kind of topology JP. There is some, this one emerged from nothing or is one still.
Yes, yes.
In that case, I'm wondering, if there is some cases where some topology changes or huge. For instance, universe cannot be emerged or transferred to part of the it's still that from your elementary constituent, you are always there. So, I mean, every different topology type.
Yes. So
Yeah, my question is there some cases where such a situation is excluded or
yes, so so in the mathematical setting, I don't know if this would correspond to your idea, but suppose we have a state x, and then we know the state space this under this TQFT, and we want to ask whether this comes from the empty cobordism like this. And if there's no restriction on this S, then it may be always possible. But if we want to say that like given this mathematical object, we might be able to put some restriction on this. For example, if we consider this n equals 1 case, and this thing is complicated enough, then we might be able to put some restriction on the genus of this. So suppose this is a knot, and if we have a so suppose this is something more complicated like this, and if we put some restriction so having this, we get this map like this, but we might be able to say that the genus of this surface must be larger than something like 2. And if we manage to get this kind of restriction from this algebraic data, then we say that if this knot cannot be unknotted, so if we have this GS equals 0, this means that this knot can be bounded by a disk. But if the algebraic restriction forbids that, then we can say that this knot cannot be unknotted. So maybe you can do something similar for the physics.
in case the algebra is not before algebra
Yeah, so we have to get something more complicated in order to treat these kind of things, and that is what homology theory is about.
Yeah, well, questions from experts are also welcome. Yeah.
How do you describe conversation?
But
How do you describe conversation is?
can you
Yeah, conversation.
quantization? I'm explaining this.
Like, yeah, to define the features.
Maybe conversational.
Features, just a line. Okay, maybe good discussion.
But why is just
Like, okay, he just briefly wrote the operational conditions.
Which one? This one?
No, you wrote the tracking.
Oh yes.
Correlation function is not proposed.
Operational functions should be bad.
But this is already compiled in theories of scale.
Yeah.
It's not symmetric. Yeah, there's not.
Perfectly good information.
There are cases that you can arrive at this kind of thing starting from C. So that's correct convention of the direction.
Questions from mathematicians or yeah.
Yeah, I have a question on algebraic aspect. Practically, in quantum field theory, we need a regularization to compute observable quantity. But there is no regularization scheme which is completely topological. So practically, we need to include method and take a limit to try to come back.
Yeah.
But it is known that the final result slightly depends on the information on the method.
I see.
And this phenomenon is called anomaly, anomaly.
I see.
And my question is that including the anomaly, is the algorithm changed or changed or?
Yeah, I think in that case, like either this, I don't know much about the other FT, but I think there are theory that does incorporate metric, like CFT does take into those accounts. So I think there are corresponding theories, and that does take metric into account. And also there are TQFT construction that uses metric, but at the end, it's proved that it is not. It doesn't depend on the metric. So.
Sorry, my question then related to that. I'm going to be totally wrong. I just want to answer something. If you regard this as path integral, you are not doing any integration of the space, right? You're just equivalent before this. No path integral. So why can you get anomaly coming from measure? Because it's like
Is it question?
yeah. Because we say anomaly, but that's practically no source of anomaly.
Yeah, so in field, like traditional conventional field theory description of the TQFT like transform theory, we need to practically include this adjective and method for suggestion. And then in my understanding, we need to specify something on some information on tangent one specify how to specify regularization of the weekend, right? And my question was include it is not that for example partial function has extracted depending on some information. And my question was even if we include that extracted, is the algebra the same or?
I don't think so. It's going to be something more complicated.
Yeah.
Yeah, I don't think so.
Yeah.
So another thing about 2D TQFT that is that it's possible to calculate with gravity. So instead of a Frobenius algebra, you get a deformation Frobenius algebra called Frobenius manifold. So in this case, you have a family of Frobenius manifold, which at one point is the original TQFT, but the different perturbation you put, I mean, you can put many different ways of coupling with gravity, then you get totally different theory. So this is much richer than Frobenius algebra. So there will be a global people.
Thank you very much. Experts on both sides.
More advanced questions. Okay, so thank you very much, Sanjay.